we did last time. So we introduced, we started talking about linear regression or linear models. The setting is that we have these data points. Each data point is a pair, one set of features or covariates xi, and then we have a target or a response or a dependent variable yi, and we want to predict yi based on xi and predict or explain different names you can give to this procedure. And we decided to model yi as a function of xi. That's like the general way of doing it, plus some noise, epsilon I. And then if this function is assumed to be linear, we assume it to be linear, then we end up with this linear model. So a general linear function would look like this, right? So f of x is going to be equal to some vector times x, and that vector has to be 1 by p if x is p-dimensional. So the function maps from Rp to R. So the feature vector has p dimensions, and the target has 1 dimension. So f of x would be beta transpose times x, and then if you plug into this equation, you would get that yi is beta transpose xi, and I'm putting tilde on top if you recall. I'll talk about that shortly, plus epsilon I. The epsilon I is the noise that we don't observe, yi and xi tilde we observe, beta we don't observe. We talked about adding an intercept. So you can add an intercept to this model to look like this by just augmenting the feature vector xi with a vector with an element of 1, and then you augment beta, the beta vector with a beta 0, which when you multiply beta transpose, like beta transpose by xi, you get the intercept as a result of multiplication for the first coordinate. Okay, that was that. We plotted things, talked about the generality of this model. So if you have like a relation, generally, like if you have a linear regression model with just one feature or one covariate, it would, if you plot the scatter plot, it would look like this. They're going to be around the line. We talked about what happens if you do the scatter plot and it looks like this. It looks like maybe a quadratic polynomial is going to be a better model. You can easily do that by just creating a new feature by like taking the square of the original feature and adding it to the feature vector. Now a linear model, so function linear in this feature vector would be like quadratic in the original sort of feature. And so that was that. And then we talked about estimation. So the key point here is that I'm posing this model, but this is really a class of models. So for every beta 0 and beta 1, you get one, like a different model. And we want to see which one of them is closer to the data, which one predicts the data well. And so this is the act of fitting the model or estimating the parameters of the model. There was one suggestion to do the least squares, so you form the deviation and then minimize the sum of squares of the deviation squared, and then you solve for beta 0 and beta 1 in this optimization problem. The argument of this optimization problem would be beta hat 0 and beta hat 1. We talked about how we can go about extending it to the general case. It just a very simple extension. So yi minus beta tilde transpose xi tilde squared. That's the squared error, and then the average or sum to get sum of squared errors. And so this depends on beta. So you find the beta that minimizes it. So the solution would be the least squares estimate or ordinary least squares estimate. And So at this point, it's an optimization problem. There are different ways of doing it. In this particular case, there is a closed form solution, which my guess is that you guys know about. We'll talk about that as well. But generally speaking, this can be solved by a numerical approach or by other means. At this point, it's a math problem. And then once you have data hat, then you can predict. So this is your regression function now. If I give you another x that you haven't seen, you plug it into this and it gives you mu hat of x, which is sort of your prediction of the response for that x, okay? Excluding the noise. So there's going to be a noise there. And I talked about how we can write this in a more compact form. So you plug in, sorry, you define this matrix, which is, let's go back down here, that contains these xi tildes as rows. And then you also have, each one also has a 1. So each row is a feature vector of one sample. Alternatively, we looked at it as a matrix whose columns are the feature vectors. So this is a more useful, both are useful, but this is going to be the one that we're going to work with for quite some time. So the features are going to be the columns. We have p plus 1 features. The first one is just for the intercept. And so this gives you an n by p matrix. Each one of these is n by 1. And in this form, you can write the regression model as y is equal to x beta plus epsilon. Okay, so this is what we did last time. And then this expands because when you multiply this x by beta, one way of multiplication is to take the linear combination of the columns of x, okay, with coefficient beta. So this, if you don't recall, review like the things that we talked about in lecture 2 probably, about column space of a matrix. So x beta is generally an element in the column space of the matrix X. And it's just a linear combination of the columns. And so that was that. We talked about these. And towards the end, we talked about the geometric interpretation. Now I have this model. We can write it this way or equivalently this way. This is like saying that y can be written as a linear combination of the feature vectors plus noise. In other words, y can be written as a component. This component, sometimes we call it mu, or the mean. So this is the signal part in a sense. This mu lies in the image of x. And there is a part which is noise that causes the entire vector to lie outside the image. And so the idea is that we want to, so estimating beta is equivalent to finding this part. So we want to find a vector like that, which is an element of the image of x that's closest to y. The least squares problem is like that. So if you try to solve this problem, so we can say least squares is I want to find y, sorry, I want to find x beta that is closest to y in distance. Okay, so an element in the image, x beta, is closest to y. And so if you minimize this over beta, that's our least squares solution. But this is sort of equivalent to what I want to mention. It's like argmin y minus mu, mu in the image. And then the output of this would be mu hat. So that would be, the relation between the two is that mu hat would be x beta hat. So if you solve the above and then compute x beta hat, that would be an element of the image. And that would be basically this mu hat. So anyone remembers what this mu hat is, like geometrically what it's called? So I want to find something in the image of x, which is closest to y. Like, what is the name of that? Yeah, so this would be projection. I might write it as like mu hat is sometimes projection of y onto the image of x. Okay, so if you project y onto the image of x, so the geometric picture is that the image of x is some subspace, y is here, and I want to find the closest vector here. So among all the mu's, potential mu's, I'm going to find one, which is going to be mu hat that's closest. And this has some interesting property. Anyone remembers? First, let me just pause. So is it sort of clear? So up to this point we talked about last time, this was like towards the end, but this is a key insight that regression, at least linear regression, can be viewed in this abstract linear algebraic way. Instead of looking at, let's say, functions, we can look at these vectors, y and xi, and then the problem reduces to a linear algebra problem, trying to explain y or expand y as a linear combination of the columns of capital X or xj's. So we want to find the middle, and the span of these best approximates y. And the span is just the image. So the problem of least squares is trying to minimize this difference, which is just the projection idea. Sounds good? Questions? Everyone happy with the geometric? So how we got there, if you recall, we just write things in matrix vector format, and then if you look at the columns of the design matrix and write things down, you'd see this geometric interpretation come up. Okay. So now let me ask you how much you remember of projection. So can I say something about this mu hat? So how do I find the mu hat, let's say, geometrically? What are the properties of mu hat? Yes.
So equal to y minus p.
P, what is P?
Oh.
I'm calling the projection mu hat, right? So I'm projecting y onto the image that's called mu hat. Can you know more about mu hat? Can you say something about what is the relation of mu hat and y? And there's a very special property of this type of projection. So you project, there's something about the error that we know. Sorry? Y minus. So E, I want to write E. E would be like y minus mu hat, let's say. Okay. Y minus E would be mu hat, right? So you can write mu hat as y minus E, I believe. So this is the definition of the error. Okay. But is there anything special about this error that I know? So this error is going to be like this guy. This is the error vector. E. Okay, good. So E is, so we know that E is orthogonal to mu hat. Okay. This is good. Do we know more? Someone in the back wanted to say something. Did you want to say? No. This side of. Is it orthogonal to more, let's say? Yes. Great. Okay. So in one step, so mu hat is orthogonal to. Sorry? Oh, yeah. This is not correct. Mu hat is inside. So these are orthogonal in the image. mu hat is in image of X. So mu hat is in the image. E is orthogonal to the image. So from these two, the first one follows. Okay, so because E is orthogonal to in the entire image and mu hat is in there, so these two imply that. So this is a special case. But the key is this property that E is orthogonal. So this we haven't proven, but I actually had to have a proof, short proof in like an optional slide if you go back. But intuitively it's clear. This is Euclidean distance, and it's like in like 3 dimensions, it's easy to see. So if I have the shortest path, then that residual vector has to be orthogonal. Otherwise, I can move it around, make it smaller. Okay. So this property can be used to easily solve the above, like find the actual solution. So we don't have to differentiate it or anything. I can just write down what this means, and mu hat comes out, or like beta hat comes out. So can I? So first, is this clear? Everyone happy? It's a very like natural intuitive notion. How can I write this down mathematically? Try to get something out of it. What does it? Yes.
The inner product of E and mu hat are 0.
The inner product of E and yeah, so that would be the top one. So that corresponds to the first one. I want to write the second, like this green box.
For any element in the image of X, each time that element is
Okay, let's call this E times mu is 0 for all mu in the image. Okay, this is good. Still a little bit abstract. Can I represent the elements in the image? Yes. Sorry? Kernel of X. So the kernel of X is a good subspace. So can you complete the sentence? So what about the kernel? It is close to. Yes, we're gonna get there. We're gonna get there. I want to like prove that basically. So this implies that E has to be in the kernel of the X transpose, but we'll see why that is. So first, let's try to write this down like more explicit fashion. So mu is in the image. Can I represent it in terms of the X matrix? What is a general like formula for element in the image of X? Looks very close, like some people have it on the tip of their tongue. Just say it. So if you go back up, so you have it somewhere here. A general form for the image, like an element in image. Span of the columns of X. That works. I'm looking at like a matrix form. X beta maybe works. So if mu is this is equivalent to there exists some beta such that mu is X beta. Okay, so if something is in the image, it can be written as X beta for some beta. This is the same as saying it's a linear combination of the columns. So I'm going to write this as E inner product X beta. This should hold for all beta. Because this way I can remove this. This is like an abstract condition, and I can control it as well. But this one I can control because this now holds for all beta. For any beta, X beta would be in the image, and vice versa. If mu is in the image, it can be written as X beta for some beta. So if this holds, this is equivalent to the following. Okay. That's sort of clear. I just wrote a generic element like this. Now this has hold for all beta. So now can I simplify this a little bit? Using transpose, like inner product is as a matrix form, right? Inner product of A and B is A transpose B. I'm going to assume that this is sort of simple, so we're going to write it down. Does this work? I'm just rewriting the inner product as P transpose times X beta. Okay, remember, like A, B, inner product is A transpose B. Now let's transpose both sides of this. I can do it in a different way. So if I want to transpose both sides, well, actually what I want to do is like do, it's equivalent. So when you write things like that, this, oh, okay, sorry. This is also equivalent to B transpose A. Okay, because of the symmetry. So instead of this, I'm going to write X beta transpose E. This is the other way around. Right, so this gives me, so how do we find this? X beta transpose E. Transpose of a product. Okay, yes, okay, this one people know. Beta transpose X transpose E equal to 0. For all beta in +1, right? So at this point, you have to argue a little bit. This is a little bit of trickiness here. So another way of saying this is, let me rewrite it like that. It's beta X transpose E equal to 0 for all beta in RP +1. You just rewrite it back. So this is like A transpose B on react as an inner product. So you could have gone from this point to this point easily by just moving X to the other side and transpose it. So this is some sort of it. But this should be clear as well. It's nothing but playing around with notation. But now this is a very interesting fact. So I have a vector X transpose E, which is orthogonal to any vector in RP +1. What can we conclude from this statement? So what is a vector that's orthogonal to every other vector? Maybe think a little bit about this. So suppose A beta is 0 for all beta. What can we conclude about A? Okay, one thing that you might try is to plug in different betas. So you can plug in standard basis vector like 1, 0, 0, 0, 0, 1, 0, 0. So I have a vector A, which is beta for every beta. So all possible vectors. So maybe thinking a little bit about this, talk to your friends about like a minute and think what this means. Okay, 1 minute thinking. Yesterday, Okay, let's come back. Hello. Hi. Any response? Let's come back. Anyone knows what the answer is? I forgot about the class. So yeah, go. Great. Why? So if you multiply anything by zero, so zero definitely satisfies this, right? Zero is the correct answer. So why, like, can you argue a little bit? So the only vector that's orthogonal to every other vector is zero. Zero definitely satisfies it because zero is plugging zero is going to be like plugging zero here, it's going to be zero. But I have this, I want to conclude that it's zero. So I have to know that there's no other vector that does this. Can you argue that? This is equivalent to actually X transpose E being zero. So the argument is simple. I just give you the argument. You can think about it yourself. Just plug in 1, 0, 0, 0, 0. That's the first basis vector here. Okay. The inner product would just take the first coordinate of this. And so the first coordinate is equal to 0. And do it for the second coordinate and third coordinate. So all the coordinates are going to be 0. Okay, just plug in different betas. Right? Different betas could be like different basis vector. And so all the coordinates are 0, so it has to be 0 vector. Okay, so this is true. Now what this is in terms of the kernel business, X transpose E is 0, what does it mean? In terms of the kernel of certain matrix. Yes.
Is that the kernel of X transpose?
So this means that E belongs to the kernel of X transpose. So kernel of X transpose are all the vectors that are mapped to 0 by X transpose. So this is a particular vector that's mapped to 0. So this has to belong to that kernel. Okay, so this like exercise was showing that E, like basically what we did, E is orthogonal to the image of X is equivalent to E being in the kernel X transpose. So if you think about this, E being orthogonal to the image, we have written this as, anyone can like say, can I say E belongs to a certain subspace? Like, what is the subspace that's orthogonal to the image? You remember, we talked about that. Great, okay, so you remember this. So E has to be, like this is another way of saying E is in the orthogonal complement of the image. So E being, like E being orthogonal to everything in the image is equivalent to saying E is in the orthogonal complement of the image. We started from that, and we end up showing that E has to be in the kernel of X transpose. And this is like equivalence. So every step is reversible. So what we showed really is that we showed that E being in the image of X perp is equivalent to E being kernel of XT. So if you've done mathematical proofs, this is just saying that these two sets are equal. If this is in this set, then it has to be in that set, which means this set is the subset of that. The reverse direction says that that set is a subset of this, so they have to be equal. So what we really showed is image of X transpose is kernel of X transpose. This image of X perp is the kernel of X transpose. That's one of the statements that I mentioned earlier. And here's a proof. Sort of clear. There's an abstract proof, but it's a very simple proof. It starts from the idea that to write down the orthogonality, and it goes through. This is general. This statement is general. But the reason why we did this is because in this case, this version, so we know that E is orthogonal to the image. This part is hard to work with, but this one is easy to work with. So this statement I can use. What I really want is this part, even if you don't care about this abstract statement, which we implicitly proved. What I want is this. Why this is important? Because I can now write X transpose times E is like Y minus mu hat in our case is 0. And this is just X transpose Y minus X beta hat, which is 0. That's mu hat. Now I can try to solve for beta hat. So that gives me X transpose Y minus X transpose X beta hat is equal to 0. This gives me X transpose X beta hat. I keep this, move this to the other side, X transpose Y. So that's the equation that this thing gives us. And this is called the normal equations, or these are called normal equations. It's a linear system of equations in beta hat that you can solve. In particular, if X transpose X is invertible, I can write beta hat in closed form. So if X transpose X is invertible, then beta hat would be X transpose X inverse, X transpose Y, which is the formula you probably know about. Okay. So if you don't recall, it just follows from this. So the error has to be orthogonal to the, the error has to be in the kernel. Another way of saying that why this is true, let me pause. There's another simple way of saying why that it has to be true. But is this sort of clear? This started from the orthogonality of E to the image. We got that, and then from this you get down here. Just plug in what E is Y minus mu hat is X beta hat. You rearrange, and you get this set of normal equations that you can numerically solve, assuming that X transpose X is invertible. And if X transpose X is invertible, this actually has a unique solution. In general, it may not. If X transpose X is not invertible, it might have no solutions or many solutions. But if it's invertible, there's a unique solution. But you can at least write it down like that. Sounds good. So have people seen how this is like? How many people have seen beta hat this formula? No one has seen this formula. 1, 2, okay. Have you seen this argument? No, okay. You have seen this argument. Okay, in which course?
In 102B.
102B, okay. Interesting. So this is a good argument to remember because it's geometric, and this formula I can also try to remember. So if you can, the argument is very simple. I want to give you another, like a very simple, straightforward way of saying why X transpose E has to be 0, because that's the starting point for this. So the easiest way to see it, even if you don't follow this, is I want E to be orthogonal to the image. And if I remember, X is like 1, X1, X2 up to XP. I'm going to write this as X0. So these are the columns. This is X. X transpose would be X0 transpose, X1 transpose, X. P transpose. And so X transpose E is really X0 transpose E, X1 transpose E, XP transpose E. So saying that this is equal to 0 is equivalent to saying that E, like X0 transpose E is 0, X1 transpose E is 0, XP transpose E is 0. So another way of saying that the same thing is like this is equivalent to XJ transpose E being 0 for all J. Basically, you're saying that E is orthogonal to every column of X. but that's equivalent to being orthogonal to the image because the image is constructed from these columns. So being orthogonal to the image is equivalent to being orthogonal to each one of these columns. And X transpose E being equal to 0 is exactly saying that E is orthogonal to every column. This is another straightforward way of seeing it. You want E to be orthogonal to the image. Why? Because the projection business, and the image is constructed as a linear combination of the columns of X. So if I have to be orthogonal to each column because the columns are in the image, but that's enough because every other vector in the image can be written as a linear combination of the elements of like the columns of X. Because I'm orthogonal to everyone, I'm going to be orthogonal to the linear combination, any linear combination. So from that, you could get this immediately. X transpose E is 0. Because geometrically, what it means is that these inner products, these are inner products of the columns of X, these are all 0. So this problem has a lot of interesting ways of seeing it, and also a good exercise in manipulating matrices and their transpose and what happens to the columns. Nice ties to regression and geometric interpretation of projection. Sounds good? So we got our beta hat after all. So that's how you can get your OLS system. This is good for us to use in our theoretical analysis, but really in practice, you're going to solve this system of equations using more efficient techniques probably. You don't have to invert X transpose X, you just have to solve the system. Sounds good? Yes.
So the dimension of beta hat is P plus 1, which is the dimension of X as well. But I mean, like the number of rows of it.
The number of columns. Yes, because we are working with X beta.
Right.
So X beta hat. So the number of columns of X and the number of elements of beta hat are the same. So X is n by n. It's always good to check the dimensions. So let's recall. So we're working with X beta. So really what usually we have is like we have a lot of like we have a lot of samples, and in this course, n is much bigger usually than P plus 1, usually. And then this is going to be P plus 1. So that's going to be beta. P plus 1. Or we can say this the other way. P plus 1. So the columns of X are n-dimensional. So this is X0. This is XP. But beta is P plus 1 dimension. Okay. Any other questions? So what else do we need to know about regression? So we now have an estimate. And is it good enough? Are we done? No. It could be done if you're happy with this. Some people don't seem to be happy. So what else remains? You can at least do prediction, a little bit prediction. So you have beta hat, you plug it in here. In what? In this way back. Yeah, so you plug it in here. Now you can predict. Right? So you have your data. So the data is like X matrix and Y. From that you get beta hat. Now you plug it into this and you can predict future data. Is this not good enough for you? For statisticians, apparently this is not good enough. In a different course, probably this would have been good enough. So what else do we need to do to be like announce ourselves as statisticians? Yes.
Do we need some sort of measurement? Of how well that equation explains the variance of the data or something?
Good.
Like in simple regression, look at R squared and stuff like that.
Right. Okay. So that's one thing that we can try to look for. How well that equation explains the data, right? So we can try to find measures that tell us how good we're fitting to the data. And we talked about that. A simple measure of that. So look for measures of how well we fit the data, like R squared. R squared came up. So R squared corresponds very closely to the mean squared error. Okay, it's like a normalized way of MSE, mean squared error. So that the easiest thing to calculate is y minus x beta hat. So that's the error that we get at the optimum. So we minimize this. This is, or the square of it. This is sometimes called the, if I divide it by n, this is the MSE. It's like 1 over n, I from 1 to n, yi minus x beta hat. So x, let's call this mu hat. This is mu hat. So y minus mu hat I. So mu hat is the fitted value. So mu hat I is the prediction basically of yi, and at the optimal value, and this is how much error remains. So this is basically the distance of yi from the regression function. You square it and average it. That's the MSE. You can look at this. One issue with this is that this is not it's not normalized. So in different problems, so it's hard to see if it's large or small. For some problem, like maybe 0.01 is large. For some problem, it's very small, depending on the scale of things. So R squared is a way of normalizing it. So that's between 0 and 1, we can compare different models. We'll talk about that. So if you divide this by something like the sum of squares of yi minus the mean, that would give you, I'll talk about this later, okay? But you already know probably what R squared is. But this is good. So we can try to work with this or R squared. Then let's leave it for a while. I'll come back to R squared. And we get a better understanding of why it is. So I think let's do it maybe just, so it would be MSE divided by, it's actually 1 minus. Yeah, let's not do it right now. Let's do it later. But this is one way to measure the fit. Okay. What else do we need? Like, or what else do statisticians care about? So you mentioned something about the variance, right? So that's a tricky problem, or like, what the statisticians care about is variance or uncertainty. That's like the better term. So they care about the uncertainty of this estimate. But that's a little bit difficult to, not difficult, but it's like, it takes a while for you to understand what it means for the uncertainty. So let's say if I want to quantify the uncertainty in beta hat. So beta hat is an estimate. It's not the true value, right? How can I measure how uncertain this estimate is? Let's say that's what statisticians often want to know, like how good it is as an estimate of the true beta. So this is also a measure of how good the model is as a whole. We'll come back to this. But how good is that particular estimate? That's traditionally statisticians worry about, because these betas would if you go back up, they tell you how different features affect the data. So beta 1, this relation. So beta 1 measures how much the feature 1 affects the yi. If I know very well what beta 1 is, I know that part of the relation very well. And in particular, one of the things that the statisticians worry about is like is this 0 or not? So if this is 0, let's say beta 1 is 0, there's no relation, like the first covariate or like feature does not affect y. And it's very good to know. So what features affect y, which ones they don't. But suppose I get like beta 1 hat turns out to be 0.001. Is this really there, or is it actually 0? We're measuring it with some error, right? That's the key kind of thing that traditional statisticians at least worried about. So I get these values, how sure like beta hats, and how sure I am about each one. Especially, and you like be sure that the ones that are really small, maybe they're 0 actually. Can we like measure, like say something about that? So for that, we need to quantify how uncertain or how variable these estimates are. So is this question sort of clear? So this is like a higher level question. So you would ask it if you thought about like, or had some thought about like the limitations of the data. But the problem is when I compute this beta hat, I just get one number. Okay, I plug in x and y, I get a vector, but these are numbers that I can calculate. There is no randomness in the solution that I get. There is no variance, right? So you've done this in practice. I give you some data x matrix, just numbers, and y, and you solve this equation or just plug into R. This is like a linear slope equation because you can invert the matrix and y and you get a bunch of numbers. Okay. So how can I say something about the variance? What do we mean by the variance? And anyone? Yes.
I think I'm wrong, but like, what about like a confidence interval?
So confidence interval is another way of like trying to characterize that variance or uncertainty, right? But first you have to understand where this variance is coming from, right? Where is the uncertainty? I get like a fixed vector. I get a beta hat, which is a bunch of numbers. You can do like an example. I don't have a numerical example here, but you get like in practice. So say the topic is like quantifying uncertainty / variability in the estimates. Let's say beta hat, for example. So question is, in practice, we get matrix, like a numerical matrix X and a numerical vector Y. Solve, let's say, star or double star and we get a numerical vector beta hat. Say beta hat would be like 0.05, negative 0.1, 0.22. Okay, let's say what I get. So where is the uncertainty? Everything seems to be quite certain. So if you understand this, you would understand confidence intervals, p-values, all stuff. Where is the uncertainty? Can you show me the uncertainty? Oh, of course, this is like a blank page. Right? Here, can you show it? Let's think about this. Yes.
Like uncertainty from like X, because like X we kind of taking like sample from like some sort of population, and also X has like the noise error term. I mean the noise. So like X varies, so whenever you try to calculate data, it kind of varies depending on your input you get, like the X you get.
This is good, but I want to like press you. So then if things vary, why did I get like a fixed set of numbers here? What could I do to get to see the variability, let's say?
Take
So-
multiple samples.
We already, sorry?
Take multiple sample of X.
Okay, yeah, so we have like x, let's say is, so we already have a sample size of n, right? So we already have multiple samples. You're on the right track. I just want you to think a little bit more. Because the issue is not that obvious to many people. It's good to think about. So I already have a sample size n, let's say. Okay, I have some sample, and then y also has. So what do I need to do to see the variability that we have, that we want to characterize?
Another set of X and Y.
Good. So we have to see like another set of n samples x and y, another entire data set, and another data set, another data set, another data set. Okay, so every time I get a different data set of the same exact sizes, I can calculate the beta hat and I get different numbers. So the variability that you're talking about is that variability, which you often don't see because you just do it once, you just see one sample. And statisticians think about this particular like capital X and Y as just one sample, one data set that you got, you could have gotten a different set. Every time you do this experiment, which often people don't do, pick n sample size n, these values will change, these values will change, the data will change. Okay. So that change is what we are trying to quantify. How much we change if we redo the experiment. So we're trying to quantify how much beta hat changes as we work with many different samples x, y of the form x, y. This is still not a very eloquent way of saying it, but I hope you understand what I mean. So the entire x and y like repeat a different experiment. Okay, it's just one sample, like one row. The entire n rows and y and like elements of y, we have to redo and redo and redo. So imagine an experiment, you go and ask people about their or like a physical experiment, you can like measure n times these different features and the response. You come back tomorrow, exactly do the same, another set of measurements of size n, and it has to be exactly n. The uncertainty that you're quantifying is going to depend on n. So if you have more, the problem changes. Do people understand now? That's what we were trying to. So this is like the frequentist interpretation. The statisticians don't care about this particular problem that you solve. They sort of care, but like the ones that are really think about these uncertainties, they don't really care about this. They care about the population version. Population version is like an abstract problem from which you can sample many, many times. Okay. So the things that we usually do, like you say yi is like xi, let's say tilde transpose beta plus sometimes write beta star plus epsilon I from 1 to n. And we made like we could like view these as random variables. That's the population abstract problem. Okay, I can sample from this anytime, like many times, or actually can compute probabilities. So probabilities, expectations tell you about what happens if you do these things many, many times. Because modeling these random variables would allow you to deal with this problem that so every time I collect a sample size n, because this is, let's say, random, because this is random, so I get a different set of like xi, x6, and y items. Okay, so this model allows me to generate infinitely many different draws from this model, and I look at chunks of size n of that data and calculate the beta hat. And in each chunk, I get a different beta hat, and then I'll look at the variability of this beta hat. Okay. So this random variable abstraction of random variables, expectations, probabilities allow you to think about this abstract notion of uncertainty. In this course, usually we treat the x as fixed, actually. The variability is going to come from this. So I'm going to assume that the next time they repeat the experiment, you're going to use the same exact x, but because of the randomness in epsilon I, the y's are going to change. So this is a simplification that we're going to assume. You're going to basically condition on this. Assume that experiment is up to me. I can set the xi's. So these are like the knobs on my device. I set them to a certain set of positions. So every time I get a sample size n, I'm gonna like construct those features, but I get a different set of y's. So for us, we're gonna assume for now this is fixed. This is random. So this is going to be a random variable for us. So random variable now is like this abstract object. It's not the one that you observed. What you observed is just, okay, so this is now a random variable. And then so y1 up to yn is a random vector. Okay, the randomness comes from the randomness. So with randomness coming from the randomness in epsilon. Okay, so and in this abstract problem, we can talk about variances, we can talk about uncertainty. Okay, so this abstract random variable is not a single number. Okay, so the one that you observed here, the numerical one, the numerical y that you observed here is just one realization, one instantiation of that. This beta hat, so beta hat is going to be defined like this. You can see it's like a function of y. So the abstract beta hat is going to be a random variable. You just observe one realization. So if you plug in one realization of y, you see a realization of beta hat, but there is an abstract beta hat. There is a random variable, like random vector beta hat. And that beta hat has some variance, uncertainty. Okay, so there is the observed. So I want to make sure that you understand this. So so we are going to have an observed / numerical y and an abstract / random variable y. Okay, the former is just one realization of the latter. So there's going to be this going on throughout the course, and you have to like be careful to understand this distinction. So in numerical problems, you calculate everything, you get numbers, but that's not what we're usually thinking about when we, in this course, usually think about this abstract random variable. You think about the numerical one and just realizations. So the same goes for beta hat. So there is a numerical beta hat, say like minus 0.1, 0.05, 0.25, and an abstract random variable beta hat. So this has an expectation a variance. We can talk about the probability of it lying in different intervals. And so there's a lot of stuff that we can do with this. With the number, we can't do much. Okay. And so confidence intervals and p-values, there's statements about the distribution of this guy. Okay, which you don't observe. It's there for you to manipulate abstractly. But I hope you get the distinction. Distinction is sort of clear. So we model the observations as coming from this abstract model. Once you're modeling things, so this is sometimes called the population version of the model. At the population level, so there are different types of population. One population can think of just a single draw as a like from the population. Here you're talking about like this n sample population. So you can think of there is a population version of the problem at the level of n samples. What I mean is that you can just draw from that many times, each time n samples. And so this vector is characterizing that population, this random vector. So what happens if you do this infinitely many times or many times? Sounds good? If you have questions, let me know. You're going to run into this issue. But if you understand this, hopefully you run into less issues. And you get a much better understanding of what p-values are, what confidence intervals are, what are really people doing. So if you understand this, then we can talk about now that there is some sort of a distribution. So if I assume something that this is random, this has a distribution, now I can talk about the distribution of this vector. I can talk about the expected value, I can talk about the variance, the covariance matrix, and then beta hat would have the covariance matrix, the individual betas would have variances, and the variances would determine the uncertainty. Okay, so how big of a variance I have for beta hat 1 tells me how variable, if you repeat the experiment many times, how variable this could be. So for example, if I end up getting an estimate of the variance of beta hat to be like 0.0001 for this one, it's a good estimate. So it means that every time I repeat it, I'm not going to see like huge fluctuations, but like minus 0.01 plus minus, let's say that's the standard deviation, plus minus something of that order. So that gives me like some confidence that this is a good estimate. If I calculate the variance of this and it turns out to be like 0.5 or like standard deviation 0.5, this is not a good estimate. They could like vary a lot. So that's where we're going. So we want to do that. Any questions about this? People are happy with. So that's the job of like traditional statisticians, trying to quantify the uncertainty by assuming some sort of probabilistic model for data generation. Sounds good? Good. Okay, so in order to do that, to do this, we need to assume something about the distribution of the noise. Okay, so I have y is equal to, let's say let's write it in the vector form. So I have this model. This is random and dimensional. Everything is in dimensions, like this is also in dimensions. This is p plus 1. So something about the distribution of this I have to assume. I'm going to assume that capital X is fixed, as I mentioned. So what we're going to assume we're going to assume two sets of conditions. What I call E1 is the E1 is relaxed. So I just assume that the expectation of this is a random vector. I'm just going to assume the expectation is 0, and the covariance is a multiple of identity, sigma squared in. So it's just saying that the variances are sigma squared for the coordinates and the off-diagonal elements are 0, so they're uncorrelated. Yes.
So just to clarify, you said that if we repeat the experiment multiple times, we're gonna get different epsilons as noise.
Yes.
This noise has a specific distribution.
Yeah, the distribution of epsilon characterizes what kind of values you would get. So that's sort of,
But if you ran the experiment, wouldn't you get different betas as well, correct?
so there's, our assumption is that the beta is fixed, that's the thing. So
Okay.
beta is fixed, X is fixed. What is gonna change is epsilon, that's the thing.
Okay, so if you're assuming the beta is fixed and you take a different sample, then the noise will be different. because
Yes.
the sample's not the same.
Yes,
If you
yes,
assume the first one is fixed, then noise is gonna be.
yes, yeah, so. It would be more natural to also assume that X varies because X is also the features. So if you assume that they're different kind of regression problems. If you think, for example, let's say you're going out there and just observing everything. That you collect the data, the features are coming. They're not in your control. You're gathering the features and you also gather the target, the response. It's natural to assume that X is also, the rows are also random. So you have random X and randomness here is going to also contribute Y. But in our case, like this traditional statistics, they assume X to be fixed. You can think of it as a design experiment. So you design your covariance. Okay, so you fix this. You're gonna like measure at this fixed level of the covariance. You just measure Y, and the randomness comes from Y. Data would be fixed because the relation is fixed. So you're assuming that there is like a real relation that you're trying to estimate. It's not going to change whenever you like repeat the experiment. Otherwise, there's nothing to be estimated. The key that this beta is the same. But good point, yeah. Does that make sense? Any questions? So the first set of assumption is this. This is minimal, and this is going to assume something at the first moment, which is the mean, and the second moment, which is the covariance. So this gets us to like certain degree. So this information is enough, for example, to calculate the expected value of beta hat or estimate and the covariance matrix of beta hat. That's enough for that. If I want to know more, so if I want to know probabilities and stuff, so what is the probability that beta hat lies in a particular set? I need to know more about the distribution of epsilon. For that, we are going to assume that we know, like we have epsilon is actually normal. Multivariate normal, it means 0, and covariance sigma squared I. So this sort of subsumes E1. So if I have this, I have the mean and the covariance matrix the same as before. But further, I'm going to assume that the entire distribution is multivariate normal. So this gives me all the information I want. So if I know E2, because X and beta are fixed, then I know the distribution of Y. If I know the distribution of Y, I also know the distribution of beta hat, because so from this we get, because beta hat is X transpose X inverse X transpose Y, and this is just the deterministic matrix. It's like A times Y. You remember if I know, for example, turns out that Y is also have, if epsilon has a multivariate normal distribution, Y will have a multivariate normal distribution. This follows from the Laplace transformation with this. And beta hat will also have a multivariate normal distribution because this is an Laplace transformation of Y. So under this function, all the quantities that we care about will have a multivariate normal distribution. And then I can use that to calculate probabilities in addition to variances and expectations. Okay, so these two assumptions are going to help us answer the questions that we want at the population level or at the statistical level. Okay, sounds good. Okay, so next time I'll come back and we actually do some calculations with this. Thank you very much. Bye.